presentation is trying to introduce one of our work about software tool development and really trying to get more people interested and to be part of it. And so that's the team and over here. And one guy is sitting there, and there's Dr. Wei He, and he left Warwick, joined MIT. And so that's the presentation. So started why we doing the energy storage. I believe everybody have heard so many things about why storage and why they store it or that storage. And apart from that, there is another driving force behind the storage in the UK. And UK has a very small network and also very low margin, only 5% generation capacity and the peak load. So every year, and the National Grid spend lots of money on balanced service. That's the figure for the past years, and come to 2018, and the figure over and 1.2 billions. It's quite big money spent on it. So they pay for contingency facilities and pay people to generation fast when the electricity need urgently. They pay people don't generate, and if they cannot digest so much electrical energy on the network. So that's, apart from technology, environmental driving force, another is about the business. If any technology can reduce the cost of balance, it will be benefit to the grid, benefit to the electricity transmission and the distributions. So then our work is focused on the compressed air energy storage. And why compressed air energy storage? And because mainly from background, and we are not chemists, and certainly will not go to battery. And also personally, and I always feel using battery for larger scale energy storage, like a few hundred megawatts, kind of feel quite sorry, because such a delicate technology we can put into mobile phone and laptop and for mobility, but we put billions of cells together, packed there, stand there for 10 years, and over 100 megawatts for this kind of application. And also end up we have to recycle or to process the waste afterwards. So that's personally, I quite prefer something and naturally can be larger scale, and naturally there's a minimum environmental impact. So that's why we focus on compressed air energy storage and the thermal storage in terms not just technology itself, and also the integration with the grid. And for this piece of work, another motivation is I attended many conferences. And the very interesting thing is almost all people present their work, first 10 minutes is about modeling, and then come to case study or simulation work and the results and analysis. So there are a lot of modeling work repeating each other, and because it's generic. So this is why we are start thinking, because our work, we did a lot of modeling work. If we can put this modeling work somewhere, and then can be shared, can be used by others, or we can use other people's model development, then it will save time and save money. So that's another motivation for this piece of work. And this is compressed air energy storage. And so for the such kind of system, and if you put a real system in place, even every single component is optimized, designed, but end up your whole system may be not optimized, cannot run sometimes. If luckily you put something there and it simply works, sometimes you put there, you spend a lot of money trying to make corrections, end up it works. Sometimes no matter how much you try, end up still it doesn't work. Mainly dynamically, they may not work together. So this is why from beginning we focus on dynamic modeling rather than just steady state modeling. And so to model this as face this way. All right, okay. And so with this complicated model, we start to search if there's any software tool we can use directly or any software platform we can use. And we couldn't find anything, we can simply use it. And also there's no kind of optimization kind of tool can be used directly with such kind of a system. So this is why we started working on this system. Okay. And so the objectives is we trying to do the whole system for compressed energy storage with thermal storage, because for any compressed energy storage, you cannot avoid thermal storage due to compression and thermal losses. And so the objective for this piece of work is trying to model the whole system and trying to make multi-physics system, multi-scale system working together, and trying to develop software can be used by industry or can be used by other research sectors. And we hope this can be a kind of open sources and then can be shared with everyone. So the methodology we used from very beginning, we tried with this system, and we pick up components and trying to make these components with standard kind. We set up standardized block. So with a standard input output and the parameter setting up and the kind of interlink between blocks. So no matter what kind of blocks you develop, you can be interlinked together. And underneath every single block with mathematical modeling, physical mathematical modeling. And then after the model being developed, we put into the library, and so anyone can use. And also you can pick up and to link them together. So because so we hope this modeling end up can be used for dynamic simulations and also for process optimization. So this end up we use MATLAB Simulink. We develop this library with all the modules, and we have a library and categories. So okay. So when you come to the two, you can see this different library: compressor, expander, and storage, thermal, storage, heat exchanger, and everything, and electrical components. And then, so with this, when you open the one particular library, you can find a different component. For example, if you found the electrical load, and then you can click on it and pick up the load type and the set of parameters, and from this electrical power system, and pick up and select it. And then you select different components and then put them together to become process. And here is an example. We have a 3 stages compression, 3 stages expansion, and also heat exchanger and storage and whole process modeling. So what we do, we pick up all the components from library and put together, conduct the whole system simulations. And so this show the pressure in the compressors and also the air pressure in the storage. And I think this is just demonstration. I think for everyone, probably that's quite familiar. And so that's also for electrical power, the rotating speed, and everything. So with this development progress, and certainly we have difficulties. So some components we can use experiment data and data sheets to verify the model, and some we cannot find any data to verify. But so with all this library model, and so we tried our best, either verify by experimental practical operation data or published data on the literature. And so put all together, we formulated the whole library. And then we put onto a website, and that's website address and estoolbox.org. And so if you are interested, you can log on to it to see what it is. So on this website, if you go to the software and you have this library, and then you can go to download, but you have to register before we download because we like to share the information with everybody. And also we like to hear your feedback if you found anything not quite right. And so when you come to the download, you have a different category. Which category you want to download? You can download the whole library, and the software you can simply go to different components if you're interested in. And then how to use it, we have a demo, there's a video, and show how to use it, how to set up parameters, how to link them together. You can watch this. And so it looks like the story and completed, but actually it's not. When we put all these components together, sometimes and the simulation crashed. And why? Because with the system, you can see the thermal, mechanical, and electrical, all different process. There are different time scale. And so when we do large-scale system simulation, sometimes become very, very slow, sensitive to parameter setting, and also sometimes crash. So from that, we start thinking if we can improve it. So the solutions we're trying to add on to see if we can use a mixed data-driven and physical model together. So that means we have this library. Suppose we trust our model, and then we use model generating data, and then use machine learning to learn, to train the black box module. End up, we have this module, and it's just kind of, for example, neural network to replace the physical model. If we put in the over big system, for example, in the whole process, you are not really interested in tank storage. You can use tank to put tank with a black box model, but you concentrate on compressor and study, dynamic study. So that makes your simulation process faster. So with this, and for example, if we have something with the 5 modules, we can pick up 2 and to become data-driven model, and then insert these 2 back together, and end up you have a mixed model simulation. And so the process to do this, and there's a kind of a flow chart to do this. And for example, that's the example we did a test, and one piston compressor case charging process, for example, and then we in this process we have electrical and mechanical and thermal all together. So we pick up one mechanical part, the electrical machine part, and did this neural network modeling. And we put this model back and simulate. So from simulation, we compared with use a pure physical model and the mixed model and the accuracy. That's the comparisons, if we believe physical model simulation is correct. And the most important thing is the simulation speed. The simulation speed become much, much faster, and you save your time, and less chance to get the whole program crashed. And so with this, to generate a data-driven model also is a complicated process. So we develop another user interface. So you can go to the interface, and then to find your go to interface to pick up components you want to model, and then get model interface to set up physical models parameters, and then go to next. Behind this, they automatically code the data-driven model to train. After training, they show the accuracy. If you're happy, then you carry on. If you're not happy, go back to train again. And after training, you feel happy. Then to generate this data-driven model, standard module for you. And then you can bring this into your simulation host system. Then, so end up, so that's have a completed two for this. And so I put this, gave a presentation. I really wish to share this and to get feedback from everyone, and also trying to bring more people into it to see if we can get a kind of a platform to share our research, and if there's no IP or kind of a commercial value or something, we can save our research time. So that's from it. Okay. And yeah, thank you.
Any question for Professor Wright?
Okay.
Yes.
Yeah.
Eric Weld, University of Duke. First of all, thank you very much for a great talk and a very exciting simulation platform that appreciate you sharing it with the world. So I have two questions. One is, I think the last bullet in your conclusions was that you had verified this with plant models, and I was just curious about the level of accuracy of these models for real-time efficiency compared to experiments. And then my second question was, with respect to compression, are you considering both isothermal as well as adiabatic compression? Right now, maybe it looks like it's primarily adiabatic. Is isothermal something that could be integrated?
Okay. So first about verifications model fidelity, that's a very challenging question, because if you don't have data, then you don't have data. So for smaller scale, it's easy. We have our own test system. We have some collaboration labs. They have a small scale, for example, a few hundred kilowatts. And then we have a collaboration with the Chinese Academy of Science. They build a 1.5 megawatts demonstration project and also 10 megawatts and at the moment. So we have some data. They certainly sensitive data, design, turbine machine design data we cannot get in details, but the operation data we can get, we can verify some. So we don't say all the model being verified, and they definitely is 100% trustable. That's why we trying to collaborate. If anyone can improve the model, and that will be benefit to the community. And so that's one thing about verifications. But I think if we have website, we have all the reference for all the model. We have reference, and there's some. If in the reference there is a date verifications, you know how this been verified. If not, and some is just a simulation, and use a steady state operation status to verify. If you from this transition to that transition, you get steady state correct. You don't know in between if it's correct. Yeah. So that's first one, okay. And the second one, in the library you can find a different operation kind of a mode. You have a different model. So we haven't developed a complete all operation mode model, but we trying to add more. That's why we contact people. If anyone has developed a model, we convert into standard modular. We can put into it, but we put a name who developed this into it, and we put pictures on the website to say who is the person designed this module. Yeah. But it's really time consuming. Yeah.
Okay. Big question. Last question before next.
Eastman, University of Massachusetts, Boston.
Yeah.
When I talk to some of my contacts in the utility world about increased penetration of renewables, it seems like their concern is not so much about the total amount of energy at the daily or even at the hourly level, but about ensuring grid stability at the second or sub-second level, like ensuring frequency and voltage stability. And in principle, of course, a big enough battery should be able to solve this problem. Can we use models like this to answer the question of how big a battery we need? And is it possible to answer the question in general, or would it always depend on the specific system?
Okay, I think it's a really good question. It's a different type of storage And I think the batteries is quite like flywheel, suitable for power kind of storage. You want to quickly, the high value I call it. If you come to electricity market, frequency service probably worth 10 times more than load shifting. So that's why if you invest on battery, and you can get your money back because you provide the service, you generate revenues through that service. But for compressed energy storage, everybody says, oh, it's a large scale and clean. But why difficult to get people to invest on it? Because you have to do larger scale. It's a big investment, and the return is smaller because if you in operation you can do frequency response, not any problem. But if you just stand still, if you start up, need 7 minutes. So end up you can only do energy type of storage. So that value in the market is quite low. So people calculated couldn't get money if in 20 years or something, and no one would like to invest on it. So it's really different type of market, different type of storage. But if you put a battery and massive battery as an energy storage, do load shifting, I just feel it's quite waste. Yeah, because if you use that for low value of market, I don't think you can get money back. It's not like a battery is cheaper than a compressor. Compressor is cheaper than battery, but just when you come to market, you cannot sell high price. Yeah.